Got another exam question walkthrough for the acids, bases and pH playlist. So we're up to number 21 now. If you want to check out the other videos in the playlist, I'll put the link to that at the top of the screen now. Hope you like the video, hope you find it helpful, and if you haven't already subscribed to the channel, I'd love you to do so. But as always, the link to the questions in the description of the video if you want to try it first. Okay, so make a start. So we've got some information about the dissociation of water. We've then got the regular Kc expression for the dissociation of water, and then we've got the simplified Kw expression. And we're asked, why is the H2O concentration not shown in the Kw expression? Well, the stat is for 100 trillion water molecules, only one dissociates. So you could say that its concentration is effectively constant. Moving on to part 2, so we've got this table of Kw values at increasing temperatures. We've got to explain why the value of Kw does increase as the temperature increases. And I've just copied and pasted the dissociation information from the top of the question, and the important bit there is the dissociation is an endothermic process, so an increase in temperature will favour this forwards reaction. Moving on to part 3, we've got to give the expression for pH, which you can see I've already done there. You don't need that little 10 in, by the way. Minus log H plus concentration is absolutely fine, but I know some people like to include it. So we've got to calculate the pH of pure water at 50 degrees C, and we've got to explain why water is neutral at that temperature. So obviously need to use the Kw expression, so there it is again, and I may as well explain why it's neutral straight away, and it's because the H plus concentration in pure water is equal to the OH minus ion concentration. So neither of those is in excess, so it's going to be neutral. So because of that, we can simplify the Kw expression to H plus concentration squared. All we need to do now is square root Kw at 50 degrees C, and that'll give us the H plus concentration, which we minus log to get pH. So there's that Kw at 50 degrees C, there's the H plus concentration, pH is 6.63 to 2 decimal places. Part 4, so we had to use this graph to work out the true pH value when the pH meter was reading 5.6. You can see what I've done, I've just gone along from 5.6 to the graph and then down onto the true pH. So it's somewhere between 5.5 and 5.6. So you could go 5.55 or 5.5. Part 5, suggest why the pH probe is washed with distilled water between each of the calibration measurements. Obviously, if you've got any previous solution on the probe, it's going to contaminate it, and obviously the new measurement is going to be inaccurate. Moving on to part 6, basically asking you, when you're doing a titration, why do you slow down whatever you're adding from the burette, sodium hydroxide in this case? Why do you slow down? Well, as you're getting close to the end point of the titration, remember the vertical line is the end point, the pH change is rapid. So if you're not slowing down, you're going to miss the end point of your titration. Number 7, state why all 3 indicators in table 6 are suitable for this titration. Remember, for an indicator to be suitable, its pH range has to lie in the vertical section. I've colour coded the 3 indicators, so bromocresol green is here, it's in the vertical section. Phenol red is here, it's in the vertical section. And thymolphthalene also in the vertical section. So pH ranges of all 3 indicators lie in the vertical section of the curve, is why they are suitable. And finally, part 8, the big calculation. So we've got volume and concentration information for sodium hydroxide and hydrochloric acid, which will obviously react with each other in a neutralization reaction. So the first thing we're going to do is work out how many moles initially we've got of the sodium hydroxide and HCl. So that's just going to be concentration times volume in deciliters cubed. So we've got 7.25 times 10 to the minus 3 moles of sodium hydroxide and 3.75 times 10 to the minus 3 moles of HCl. Sodium hydroxide in excess, there'll be some of that left, there'll be none of the HCl left. So why does the sodium hydroxide drop down to 3.5 times 10 to the minus 3 at the end of the reaction, the final moles? It's because that many moles of it will react. So because we've got sodium hydroxide left over at the end of the reaction and therefore hydroxide ions, we need to bring in the Kw expression, and we're going to rearrange that for the H+ concentration so we can get the pH. So that rearranges to Kw over the hydroxide ion concentration. So we just need to sub in some values and get the H+ concentration, but just be careful. These are moles. We need to turn them into concentration, which is why I have highlighted the combined volume of the solution is 61.25 centimeters cubed. So we need to divide the moles by the volume in decimeters cubed to turn it into that concentration. So the OH- concentrations come out as that. So Kw at 25 degrees C divided by the OH- concentration gives us that. For the H+ concentration, obviously that's moles per decimeters cubed, so we just need to minus log that to get the pH, which comes out at 12.76. So very well done if you got that right.